Hello everyone, welcome to our channel. We will continue our mathematical optimization series with the seventh video. In the previous videos, we showed many concepts implemented on Groby and the GrobyPy package on Python. If you haven't watched it yet, you can watch it with the link above. In this video, we will talk about CPLEX basics while remembering what the linear programming is. We also show how to code them using the docplex package in Python. In the previous video, we showed how to install CPLEX Optimization Studio and docplex package on Python. If you didn't install the software, you may want to check it out with the link above. Let me first briefly remind you the linear programming. The linear programming is a widely used field of optimization for many decades. Many practical problems can be represented by using linear programming. It's a special case of mathematical optimization. Linear programming is a method to achieve the best outcome in a mathematical model whose requirements are represented by linear relationships. In this type of optimization, there exists a linear objective function and linear equality and/or inequality constraints. Constraints make a feasible region, and we are trying to find the best point in the feasible region. Recall the standard form of it. The standard form is the usual and most intuitive form of describing a linear programming problem. It consists of the following parts: a linear function to be maximized or minimized, and the problem constraints of the following form. Other forms, such as maximization problems, problems with constraints on alternative forms, as well as problems involving negative variables, can always be rewritten into an equivalent problem in the standard form. Let us create an example of linear programming and code it in Python using docplex package. Assume that we have a minimization problem with the objective function 5x plus 4y. And there are constraints that our solution needs to follow. We have three problem constraints and two non-negativity constraints. First one is x plus y greater than or equal to 8. Second one is 2x plus y greater than or equal to 10. And the last one is x plus 4y greater than or equal to 11. As I said, we have non-negativity constraints for x and y. Let's have a look at the feasible region created by the constraints. In the graph, we have 5 inequality constraints, where 2 of them are two non-negativity constraints and 3 of them are the constraints above. Namely, the orange line represents 2x plus y greater than or equal to 10, and the blue line represents x plus y greater than or equal to 8. And the green one represents x plus 4y greater than or equal to 11. The gray area shows the feasible region for our problem. Now we will show our objective function line in the next graph. This graph shows both the feasible region and the objective function line. With the current graph, the solution is not feasible since the objective function line, which is red, and the feasible region are not intersecting. We aim to intersect both of them and resulting in the minimum objective function value. To do that, we need to pull the objective function towards the feasible region. In the third graph, the objective function intersects with the feasible region. Actually, it is the optimal solution. We can calculate the objective function value by using analytical geometry. Also, we can code it and find the value of the objective function and the corresponding x and y values using docplex package. Let us move to the coding part. First things first, we need to import the model function from docplex.mp.model. You should remember this from our previous video in this series. After importing the package, we now create our model. The function model is a model constructor. We can give a name to our model. Note that it is not necessary to give a name to the model, it is optional. The function returns a new model object, and initially the model contains neither variables nor constraints. Let us define our model as opmod and give a name linear program. In the next step, we add decision variables to the model. We use the continuous var function as we have two continuous variables. There are many optional inputs for this function. We can specify lower and upper bounds. We also can give a name to the decision variable. We define our x and y decision variables by stating their names and corresponding lower bounds. The next step is adding the constraints. We use model.addConstraint function to add our three constraints. Remember that we have already added the non-negativity constraints when we define the decision variables. We add three constraints by using the function. First, x plus y greater than or equal to 8. Second, x plus 2y greater than or equal to 10. And third, x plus 4y greater than or equal to 11. If our model would have an equality constraint, then we only need to write equal instead of greater than or equal to. In step 5, it is time to define our objective function. We use model.setObjective function to specify the objective function. There are two inputs, first the sense and second the objective function as an expression. For our model, we define our objective function as 5x plus 4y, and the sense is min. By using printInformation function, we can examine the model we created. As we see in the output, we created a model named linear program. It has two continuous variables and three linear constraints. Our aim is to minimize the model, and the type of the model is LP, which is linear program. Now we are ready to solve our model. We will use the solve function. As the name suggests, it solves the model. Note that the algorithm used for the optimization depends on the model type. Let us solve our model by writing optmod.solve. As you see, the model is solved by using CPLEX optimizer. You can see the details regarding the solution. In the line, you will see optimal objective function value is 34. As a last step, we will output the result and the corresponding decision variable values. To do that, we will use printSolution function. When we call the function, the output is the following. Our optimal objective function value is 34. The decision variables x and y are found to be 2 and 6, respectively. Thank you for watching. Please like our video if you like it, and do not forget to subscribe to our channel. If you have any questions, please let us know by writing a comment below. We will be happy to help you. Thank you.